Well, friends, today we're talking about section 1.3, linear functions. And what I have here is a table of data, and we have t and w, and certainly w is a function of t. For any given t value, there is only one w value that emerges. And the question is, how can we show if this is a linear function? And maybe we could say, what is a linear function? And the answer is a function with a constant rate of change. So what are we going to have to do to determine this constant rate of change? We're going to calculate the rate of change, which is really the slope. Now, in order to do this, I have to do this over 3 different intervals. So I could go from -1 to 1, from 1 to 2, and from 2 to 5, or really any iteration in between. But we're just going to calculate 3 different intervals. If they all coincide, then at the University of Michigan, we can conclude that we have a linear function. Well, we see that every single one of the points that I chose have a slope or a rate of change of 3.1, and so our function is indeed linear. When we talk about linear functions and we want to make equations for linear functions, we have 3 primary forms. And I guess the first one would be slope-intercept form. Which you all know as y equals mx plus b. And I love that, except for the fact that I'm not always going to have x's and y's. And, you know, in a real world scenario, typically I'm starting out with something. And so I'm going to say that I'm starting with some quantity q naught, my starting value. My overall quantity will be here, and that's going to be m. So there's our slope times t, my input value, and so we can say that q is equal to some function of time. I mean, both of these are really the exact same thing. I've just mixed the two up. Here, b is the same as q naught, m is still our slope, and our variable is x and then t. Slope-intercept form is great. If I give you an intercept, if I give you a slope, I can make that line very quickly. So suppose we go through, start at, we'll say 0.7 and increase by 3 for every 1 x increases. And I can certainly say that our slope is 3, that's increasing, and I guess maybe say q increases by 3, so I can say 3 over 1 is my slope. And q, my unknown quantity, is equal to 7, my starting value, plus 3 times x in this case. Okay, so that's slope-intercept form, not a great stretch of the imagination. But that's not my magic bus. My magic bus is point slope form. And what point slope form allows me to do is I can take any point in space and I can make an equation through that point. So let's say we go through the point 3, 7 with a slope of -2. Point slope form, I'm going to use the same variables q and t. We can write this as q minus q naught is equal to m times the quantity t minus t naught. And I guess just to relate it back to what you know, you saw this is y minus y naught is equal to m times x minus x naught. And the variables don't really matter, but I want us to get off of x and y and onto looking at things in maybe a more meaningful way. Now, as much as I love this, what we really typically want to do is we want to have q as some function of t, which means I'm going to have to get q alone. And so where we're going to go most of the time is q is equal to m times t minus t naught plus q naught. And what I did is I added q naught to both sides of the equation. Now, let's take this out for a spin with this specific example here. And so we'll have q as our variable. M is our slope, -2. T is our input variable. T naught is 3 plus 7. And what I love about this so much is look what happens when I plug 3 in, murder occurs, and I'm left with only 7. If I did want to know that initial value or convert this into slope-intercept form, we could do that super easily by distributing through. Q is equal to -2 t plus 6 plus 7, and so -2 t plus 13. And there we have our initial value. Just like we would have with slope-intercept form. If I give you a point and I give you a slope, I expect you to use point-slope form. I do not appreciate algebraically solving for b. I think it is too cumbersome and just not an efficient usage of your time. Our final form for equations that are linear is standard form. And what this looks like is ax plus by equals c. I guess I could use q and t as well. We could say at plus bq is equal to c. And a, b, and c are constants. Now, where does standard form normally rear its head? When we have some sort of constraint equation. And in this case, a constraint is just some limiting factor. Maybe money, maybe time, maybe resources. But I think money is a very reasonable way to play. And so let's start out with $10 to buy snacks. Okay? So if I'm going to spend $10 to buy snacks, we can have $1 for fruit snacks, or $1.50 for cheese zits. They're disgusting. So, and the idea is we're going to spend all of our $10 here. Let's use F for fruit snacks. Let's use C for packages of Cheez-Its. And so we're going to make a constraint equation. 10 is equal to, well, 1 times the number of packages of fruit snacks that we buy, plus 150 times the number of packages of Cheez-Its that we buy. So here we're in standard form. Now, I want to continue a little bit more. Suppose express the Cheez-Its as a function of fruit snacks. What am I asked to do here? I want this to be my output, this to be my input, which means I am going to solve for Cheez-Its, and then we should be done. So I'm going to subtract fruit, and I'm going to divide by this 1.5. And so C will equal to 10 minus 1F. I'm just going to keep it like that for the time being, over 1.5. And as much as I love this, and as much as I've satisfied this relationship, what I don't really clearly see here is the slope. So what I can say is that I'm dividing each of these quantities, 10 over 1.5 minus 1 over 1.5